At this point, we need to address a certain question. Here we have our equation that the magnetic force is equal to QVB times the sine of theta. But what happens if the charge is negative? Very obviously, if you have a negative charge, that's going to create a negative force. Well, what do we mean when we have a negative force? We just mean that the force is in the opposite direction. So, let's look at this charge here. This charge is coming out of the board. So basically it's coming out of the page toward you. You've got a magnetic field that is pointing to the right. So if it's coming towards you, magnetic field points to the right, then that gives you an upward force. But if Q is negative, then that force reverses. So even though the right-hand rule says up, Q reverses that, and so now your magnetic force is down. So the right-hand rule, bottom line, the right-hand rule works for all currents as well as all the motion of positive charges. If you have the motion of a negative charge, use the right-hand rule still, but then reverse that direction. Okay, now here's something really cool that happens. You have a moving charge that's moving off to the right. Well, if there's a magnetic field that's a uniform magnetic field that's going into the board, you can see that all the way around here. You just have a whole region of magnetic field into the board. Then that's going to create a downward magnetic force, causing it to accelerate and turn it to the right. Well, now its velocity has changed. If you do the right-hand rule again with this new velocity, you're going to find that the force has changed direction as well. You're going to find that this keeps going on, and the force ends up going all the way in, pointing into the center of a circle, and your charge just moves in a circle, which means that we're back to centripetal or radial forces and accelerations, in which case it would be your magnetic force going to equal mass times the velocity of your charge divided by the radius. Now, you can go back to chapter 5, which discusses more about radial or centripetal accelerations for this. But this is a very important point for this reason. Let's go back and visit the Earth's magnetic field. Okay? I mentioned in the first video that it's good that the Earth has a magnetic field, because if we didn't, then it would cause a lot of harm on life on Earth. Let me explain that a little bit more. Here's the sun. Not the greatest sun in the world, but hey, it works. Every once in a while, the sun will spew a lot of high energy particles. And these high energy particles, if they were to come to the surface of the Earth, would harm life and possibly even destroy all life on Earth. However, because of the molten core of the Earth, the rotation of that molten core creates a magnetic field around the Earth. So when you have highly energized charges, electric charges, passing through the magnetic field, what happens? They start to go and move in a circle. So they start moving in a circle. However, there's also a component of that velocity which pushes it forward, and so those charges are safely deflected away. Okay, well, they're deflected away, but wait a second, they're congregating towards the poles. They're still high energy particles. How do you get rid of that energy? How do you keep it from hurting life at the poles? Well, when you get all of these charges just gathering up here near the poles, they bunch up in the upper atmosphere, high up, way above where we live, so it's fine. But then these charges release that energy in the form of light. This is what causes the northern and the southern lights, also known as aurora borealis and aurora australis. So really the aurora is nothing more than the release of energy from particles that came from the sun, which were deflected by the Earth's magnetic field. Pretty cool. I think that's a really fun application of all this. All right, let's finish up this video by summarizing our right-hand rules. We saw in our first video that if you have a current running through a wire, you use your right-hand thumb and point it in the direction of the electric current, then your right-hand fingers will naturally curl in the direction of the magnetic field. The second right-hand rule says that if you take your fingers and point them in the direction of your current or the charge's velocity, then you take the right-hand fingers, point it in those directions, curl the fingers so that now they're pointing in the direction of the magnetic field, then your thumb will be pointing in the direction of the magnetic force. Okay? So, problem solving for magnetic fields, three main things to remember. The magnetic force is always perpendicular to the magnetic field. And I'm going to also say the electric current or the velocity of the charge. It's going to be perpendicular to both the magnetic field and current, or to the perpendicular to the magnetic field and charge's velocity. Second thing to remember, the right-hand rule is only useful for determining the directions. You cannot find the magnitude using the right-hand rule. In a similar note, the equations that were given in this chapter only give the magnitude. That's it. Equations in the chapter give the magnitude only. To get the direction, you have to use the right-hand rule. If you want to combine those two, we can, but that involves calculus using a cross product. If for those who know calculus, excuse me, I drew that wrong. You use a cross product of the length and the magnetic field, or for a charge, it would look something like this. That's the calculus version of the equations that we have dealt with. I'm not going to show you how to use them. If you want to use them as a calculus student, by all means. But this is the only way to do both direction and magnitude in the same equation. So I'm going to erase all this because it's irrelevant. The way we teach in this course, you determine the direction using the right-hand rule, magnitude using the equation.